All right, guys, today we are going to talk about correlation coefficients and the correlations of data. So first we have our definition here of a correlation coefficient. It is a number from -1 to 1 that represents how closely a set of data fits a straight line. So when we're talking about the correlation, we're talking about the relationship. We have different strengths and we have different directions. So first we're going to talk about the direction. All right. So the first direction that we have is saying as x increases, which means as you're going to the right, y increases. Your data goes up. So as you move to the right, it goes up. That's like a positive slope. This is called a positive correlation. Okay, so as x increases, y increases, that is a positive correlation. As we're going this way, your data is going up. All right. The next one over here is when x increases. So as you're going to the right, your y decreases. Okay. That's like a negative slope. As you move to the right, you're going down. This is called a negative correlation. Okay, because as you move to the right, the data is going down. The data points are going down. And the last one looks like this example graph, and it's when x and y seem to have no apparent relationship. So we can't really tell. With some of them, as you move to the right, some are going down, some are going up. There's no real relationship. We say there is none or no. I'm going to write none here. We also say no correlation. All right, so that's the first thing that we're going to look at when we're talking about correlations is the direction. So positive when x increases, y increases, negative as x increases, y decreases, or no correlation, none. The next thing that we need to know when we're talking about the correlation between data is the strength. Okay, so as we see in the definition, correlation coefficient is a number from -1 to 1 that represents how closely a set of data fits a straight line. All right, so we have a range here. We have R is what represents the correlation coefficient going from -1, -0.8, -0.3, 0, +0.3, +0.8 to +1. Okay, so you can see this below on this down here, but I'm going to label these on the graph so you have specific examples. If your correlation coefficient is -1, that is what we call a perfect negative correlation. Okay, every single data point in this set is going to fit exactly on a line with a negative slope. So I could write a y equals mx plus b equation, and every single point of data would fit exactly to that line. And it's going to have a negative slope. Okay, every single point. Can't be one slightly out of place. For perfect, it would have to exactly be on a line. Okay. The next we have is R is -0.8. And as you can see, this set of data, this right here, is not exactly on a line, but for the most part, as you're moving to the right, the data is going down. Not every single one, but for the most part, you can see that as you're moving to the right, the data is going down. That is a negative direction, as we talked about before, and we call that a strong negative correlation. The closer to -1 this number is, the stronger it is. So that's a strong negative correlation. A good correlation coefficient for that would be -0.8. Then we move one over and you can see that with this data here, it's not as good as this one, right? But it still has a generally negative correlation. As you're moving to the right, it looks like most of the data is going down. Not all of it, but most of the data. But it's not great. So we call that a weak negative correlation. And when you're talking negative numbers, the closer to 0 you are, the weaker that correlation is. Okay, so it's definitely not a straight line. It's not even kind of close, but you can see a pattern. You can see a pattern, so I would call that negative. Then when you have R is 0, this is when there is no correlation. So if you're looking at a set of data on a graph and you're like, well, I could kind of make a case for positive, but I also see some for negative. It's nowhere near a straight line. It kind of just looks like everything's randomly on the graph. That's going to be no correlation, and the correlation coefficient is going to be 0. That means we cannot find any sort of pattern whatsoever among the data points. The relationship between the x and the y, it seems random. That is when it seems random. Okay. Next one, moving through here, when we have a correlation coefficient of 0.3, something that looks like this graph on here, it's nowhere near a straight line, but typically you can see that as you're moving to the right, the data points are going up. That is going to be positive. The direction would be positive, as we said above. And we're going to call that a weak positive correlation. All right. As you move to the right, we're getting closer to 1. That looks like it's closer to a straight line. My correlation coefficient is 0.8. It definitely is positive. As I'm moving to the right, my data points are going up, and I'm going to call that a strong positive correlation. The last one on here, this is going to be a perfect positive correlation. I could write an equation y equals mx plus b with a positive slope, and every single point, every single data point would fit exactly on that line. It has to be every single one to have a correlation coefficient of 1. Okay, so now on here you have some examples of not only what the correlation coefficient would be in terms of the direction and the strength, but what the graphs look like. So below it, it just has that same thing, and it's not using the graphs. It's talking about -1 would be a perfect linear relationship. Okay, and then you move into strong, weak when you get back to 0, and then moving towards the right, perfect and strong again. All right. So the next section, it says the table shows correlations for the 4 graphs below. Match each graph to its correlation coefficient. So we have 0.72, -0.9, 0.96, and -0.42. You have no way, without any tools, without any graphing calculator, something like that, to actually know what these correlations are right now. We are just going to use the process of elimination. We're going to make our best guess. Okay, so I want to first label, okay, what types of correlations we're looking with on the graphs. Okay, so first of all, this one is definitely, when we're on graph A, this is definitely positive. And it's more on the strong side. Okay, as you're going to the right, the data points are going up. It's not a perfect line, but it looks pretty close. Okay. This one is definitely going to be negative. It's usually easiest to see the direction. So as we're moving to the right, these are going down. It looks pretty strong, negative, right? There's just these 2 points out of there, but that looks pretty strong. Over here, we've got a positive, maybe somewhere between strong and weak. And over here, this is definitely a negative, but it is weak. So it's good to kind of get an idea based on the graphs first before you start doing the process of elimination. So then I look at the correlations that I have, and one thing that jumps out to me is I have 2 positive and 2 negative, which is good because within the graphs, I have 2 positive, 2 negative. So I'm going to start with the 2 positive ones. So that's going to be graph A and graph C. And that's going to be 0.72 and 0.96. So now I need to decide which one goes with which. One of them is going to be graph A, one of them is going to be graph C. So looking at the numbers, 0.96 is very close to 1. So that's going to be the stronger of the two correlations. So I look at the two graphs, A and C which set of data looks like it's in closer to an exact straight line. That's going to be this right here, graph A, which means that graph A goes here and graph C goes here, which makes sense because 0.72 is pretty strong, but not as strong as graph A. All right. Next, we're going to look at, we've got negative 0.9 and negative 0.42, and we've got graph B and graph D. So we can see with these that the negative 0.9 is going to be closest to the straight line because -1 would be a perfect straight line with a negative correlation, a negative slope. So if I look at graphs B and D, decide which one is closer to a straight line, and that's definitely going to be graph B. It has these 2 points off to the side here, but all the rest of them look like they're going to be on that straight line. So graph B is going to match up here, which leaves us with graph D, which definitely looks like a weak negative correlation. So again, when you're doing this and you're given all of these, I would definitely use process of elimination. Think about what the numbers mean, looking back up here if you need help with that, and thinking about what the graphs mean. Again, this middle section that I filled in is really going to help you with problems like that. All right. Last thing we want to look at is we have some word problems. So it says pick the appropriate statement for each survey and give a reason for your answer. Number 8, in a survey, the correlation coefficient between engine size and fuel economy was found to be -0.9. And then you have 3 options. As the engine size increases, fuel efficiency increases. There is no evidence of a linear relationship between engine size and fuel efficiency. And as the engine size increases, fuel efficiency decreases. So here is what we're going to look at. This number right here. Okay, the negative tells us that this has a negative correlation, which means as X increases, Y is decreasing. That's what that negative correlation means from our notes. Okay, being 0.9 means it is strong. Okay, that means it's strong because that's close to 1, close to -1. All right. The closer to 0, the weaker the correlation. The closer to 1 or -1, the stronger the correlation. Okay, so our X and our Y are two things that we're comparing. Is engine size would be X, and fuel economy would be Y. Okay, so this is saying here, the bigger the engine, so as X is increasing, fuel economy goes down, which makes sense. If you know anything about cars, right now that makes sense. Okay, so then I look at A, B, and C, my options, and the one that fits that is C right here. As the engine size increases, fuel efficiency decreases. Did I write economy? Yeah. I meant efficiency, fuel efficiency. There we go. All right. And the reason for the answer, the negative means is one variable increases, the other decreases, and 0.9 is close to 1, so it's a strong correlation. All right. In the next one, in a survey, the correlation between the numbers of hours per week students spent studying and their performance in an exam was 0.7. And it gives us the 3 options. So before I even read these, I'm going to examine that 0.7. We're going to talk about what it means. So first of all, it's positive, which means as X increases, Y increases. And we're talking about number of hours a week students study being X. We have some, and the performance on their exam, which is Y. So as you study more, you do better on your exam. That's what that's saying. The number 0.7 is not perfect, but strong. 0.7 is closer to 1 than it is to 0. So that's a pretty strong correlation. So then we find the A, B, or C that fits that. A says as the number of hours spent studying increases, student exam performance increases. There we go. That's going to be our answer. And reasons for our answer: positive means as one variable increases, the other does as well. The more you study, the better you do. 0.7 is closer to 1 than 0, so it is a relatively strong correlation. We could say that there is a relationship between the two things. All right. If you have any questions on correlation coefficient, make sure you come to office hours, try the practice, and then go ahead and do your 4-question quiz.